In this video, we're going to talk about a specific type of intermolecular force that's called hydrogen bonding. Hydrogen bonds. So, first things first. What do we need? Why is there the need to explain hydrogen bonds? Well, let's look at some data here. These are for binary halides. Okay. So, meaning binary, meaning two elements, where one of them is hydrogen. So across different rows of the periodic table. So we got boiling points here on the y-axis, and let's look at the general trend for oxygen, then sulfur, selenium, tellurium. If we double check the periodic table, that'd be oxygen, sulfur, selenium, tellurium, and then for fluorine, chlorine, bromine, iodine, fluorine, chlorine, bromine, iodine. So as we go down these rows, what's the general trend? Well, we can see that for row 2, 3, and 4, the boiling point is increasing. It's a trend going upwards. However, there's this kind of weirdo with oxygen and with fluorine. When oxygen and fluorine is bonded to hydrogen, the boiling point is much, much higher than the boiling point of hydrogen bonded to any other compound in rows, in columns with oxygen and fluorine. So why? Why is this boiling point so much higher? Well, we've learned that boiling points are higher when molecules have more intermolecular forces, because therefore it takes more energy, more heat in order to boil that compound, to convert it from a liquid to a gas. So what's so special about the intermolecular forces in these molecules, though? They have what are called hydrogen bonds. So let's get into the details, into the pictures, into the images of what a hydrogen bond actually is. So for water, okay, if we drew the Lewis structure for water, we know that it would look something like this. I'm not going to draw the lone pairs on oxygen, and you'll see why in a second. We know that water is polar. Oxygen is more electronegative than hydrogen, so we're going to have a slight negative charge here and slight positive charges here. Therefore, if we put another water molecule next to this one, we know that this negative charge is going to want to be next to a positive. So if we were to draw another water molecule, it would arrange itself like this next to this molecule. Because here we would have a slight positive, negative, and then another slight positive here. Since there's opposite charges near each other, there's going to be a force of attraction here that I'm going to label this blue dotted line. This is a force of attraction, an intermolecular force, because it's between two different molecules. Here's one molecule of water, here's another molecule of water, and since there's a force between these two, that's an intermolecular force. This particular force, okay, this represents a hydrogen bond. Now, usually when we think of the word bond, we're talking about an intramolecular force. But in this case, it's not actually an intramolecular force. So a small thing to watch out for, kind of a misnomer, kind of not appropriately named. Remember, small review, intramolecular forces are bonds or forces within molecules. So for example, this would be an intramolecular force, this would be an intramolecular force, this, and this. However, this force between these two molecules is an intermolecular force, or an IMF. Why does this form in water? Why does this intermolecular force actually exist? Well, there's a few things that we need to know about hydrogen bonds. Okay? They only occur, you only see them in polar molecules. The example that we just looked at of water was a polar molecule. These molecules are permanently polar. They're always polar. They're always going to have a slight positive and a slight negative end. So these are only occur in polar molecules, and therefore they are permanent. Okay? They're always there. They're always present. Water will always have hydrogen bonds no matter what because of the structure of the atoms. The other thing we need to know about hydrogen bonds, and this is the most important fact, they only occur in molecules when hydrogen is bonded to an F, an O, or an N, a fluorine, an oxygen, or a nitrogen, okay? Sometimes called the Fonz, okay? And old TV show, no one's going to get that reference in here. But anyways, Fonz, if hydrogen is bonded to a fluorine, an oxygen, or a nitrogen, then hydrogen bonding can occur. Why is that? What's going on? What's so special about these three elements? Okay. Well, all three of these elements, if you think about where they are on the periodic table, they're all kind of up in this top right corner. And we know that up in the top right corner, all these atoms are very electronegative. They really want electrons. As a result, since they're super electronegative, they will pull electrons away from whatever other atom they're bonded to. So for example, if we have a hydrogen bonded to a fluorine, hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen, we know that all three of these atoms really want to steal electrons. So they're all going to be slightly negatively charged. And therefore all the hydrogens will become slightly positively charged. Therefore, since we've made a polar molecule, a polar bond, this, and this will all try to arrange themselves so that positive and negatives are next to each other. And the more that we have of those, the more intermolecular forces we have, the higher the boiling points and melting points are going to be of those compounds. So, for example, if we looked at a question like this, can methane, CH4, form hydrogen bonds? Explain. Well, let's think about the Lewis structure for methane. It's CH4. Okay. So when we're asking ourselves, could the molecule have hydrogen bonds? Remember, in order for something to have hydrogen bonds, the hydrogen must be bonded to a Fon, a fluorine, an oxygen, or a nitrogen. Here, we have hydrogens, but they're not bonded to carbon. Excuse me, they're not bonded to a fluorine, an oxygen, or a nitrogen. None of them. It's bonded to carbon. And what's unique about that? What's so significant? Well, therefore, carbon and hydrogen's electronegativities are very similar. So this bond is not very polar. We can almost call it nonpolar. Every single one of these bonds is nonpolar. So there's going to be no charge that can be formed, no positive, no slightly negative charge that can form. So hydrogen bonds can't exist in this molecule. What about another example? What about, we talked about this already, but HF, hydrofluoric acid. Can this compound have hydrogen bonds? Well, do we have hydrogen bonded to a fluorine, oxygen, or nitrogen? Yes, we do. We have hydrogen bonded to fluorine. Well, what's significant about that? Fluorine is very electronegative. It's going to want to pull on these electrons in this bond, pull them closer to itself. So if there's more electrons on fluorine, this will be slightly negatively charged, and this will be slightly positively charged. So how would these molecules arrange themselves if there are many of them next to each other? Well, we'd have HF next to each other, and since fluorine is slightly negative, it would want to be next to the slightly positive molecule of another HF. So, we'd have like HF here, slightly positive, slightly negative. And then we might have a fluorine here bonded to a hydrogen here, because this is slightly negative and slightly positive. The one thing that we need to note is the way that intermolecular forces are usually drawn are with dotted lines. So here, boom, 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 that would represent an intermolecular force. More specifically, so again, green equals hydrogen bond, which is a type of intermolecular force. And that allows us to distinguish between the intermolecular forces, which are drawn as solid lines. So this would be a representation of 3 hydrogen fluoride molecules, some HF molecules next to each other. And we would say that yes, hydrogen bonds exist because hydrogen is bonded to a very electronegative element, fluorine in this case. Let's tie that back together with the data we looked at originally. What's so special about the boiling points of these two compounds? Ooh, well, they both have hydrogen bonds. Here, water we talked about, the Lewis structure, okay, has hydrogens bonded to oxygens, so that's going to form a dipole, which can form intermolecular forces, and more intermolecular forces means higher melting point and boiling point. And HF, we just did as an example, does the same thing. It can form a dipole because hydrogen is bonded to very electronegative element fluorine. So there's more intermolecular forces, so the boiling point is going to be higher. What about if you go from oxygen down to sulfur, H2S? So the Lewis structure here is still the same as water, but just with sulfur in the middle. But look, the boiling point is so much lower. It's about -60 compared to 100 degrees Celsius. It's so much lower. That must mean, since this has a lower boiling point, it must have very few intermolecular forces, IMFs, compared to H2O. And why is that? Well, can it form hydrogen bonds? No, it can't, because sulfur is not fluorine, oxygen, or nitrogen. It's not way more electronegative than hydrogen, so we would not get a dipole like so. These intermolecular forces of hydrogen bonds would not form, so it'd be easier to melt it. We'd have a lower boiling point.